Hi gents, we're gonna continue on with 4D. I got some questions in from people just asking me if I would do number 19, which I think I'd suggested that you go and do. So we will have a little look at that. It's page 59 here. We have an airplane which is flying at maximum speed. Is traveling due west at 100 kilometers per hour. It is partly helped by a wind blowing at 20 kilometers per hour in a direction 30 degrees north of west. So we've got 30 degrees north. Whoops. Let's go again. North of west. Okay. That's 30 degrees. So of course the plane is going to have to be going in that particular space there. Okay. This is very much not to scale, but we've got 100 there. And here we have the vector, which is of the wind. And this here is the vector of the plane. And this is the vector of the plane relative to the wind. Okay, let's fill in some of these. Values. So the plane itself, that's the easiest one. That vector is, remember, it's going left, and we're told that it's going 100 kilometers an hour, so it's minus 100i, and no j's. Now the vector of the wind, we're told that it is going at 20 kilometers per hour. So it's going to be 20 cos 30i plus 20 sine 30j. Now you just need to be a little bit careful of that. What it's really doing is it's going to the left, so it's going to be minus, and it's going up, which is going to be plus. So if we just tap that into a calculator, I think that's root 3 over 2, so I think that's going to be minus 10 root 3i. Just check that. 20 cos 30. Yeah, 10 root 3i, and it's going up. So that's going to be, that's a half, so 10 j's is what it's going to be going. And it's asking us there about what's the maximum speed of the airplane in still air. So what do we know? We know that we have the vector of the plane relative to the wind is equal to the vector of the plane minus the vector of the wind. So we're going to start with this, and we're going to take away that. So we're going to have minus 100 i's, and then we're going to take away this. When we take away a negative, we're adding it on. So that's, adding on 10 root 3, and those are all the i's that we have. And we are then going to do this number here, our j's, so that's the vector for the plane, and we're going to subtract the vector for the wind, so minus 10j. Okay, and it's saying what is its speed, so it's really just asking what's the magnitude of the vector there. So it is the square root of minus 100 plus 10 root 3 there. Plus 10 root 3. Is that squared added to minus 10 squared. Okay, we'll throw that all into the calculator. Minus 100 plus 10 root 3 squared plus 10 squared. Okay, and that for me is coming out to be not a particularly nice number. It's coming out as 83. I wonder, yeah, 83.28. Don't know if it said to however many decimal places, but actually, yeah, there's not too much that we can do there. We might be able to write it minus 100 plus 10 root 3. Let me see if I square that. Does it write it in a nice way? particularly on side on my calculator, so we will just leave it. We will leave it like that. So that's our answer to question 19. I'm just going to pick out another one here for us to do as an example. Okay, the next one that we'll do here is yeah, we're still on that. Is we'll do 25. That looks like a tough one. That's towards the end as well. So it says a man wishes to swim across a river which is 36 meters wide. The river flows with a velocity of 2 meters per second, parallel to the straight bank, and the man can swim at 1 meter per second. If he heads at an angle alpha to the upstream direction, and his actual velocity is at an angle theta to the downstream direction, show that something trigonometric is true. So let's just think about this, that the water is going at 2 meters. Okay, obviously there's a gap of 36, but we won't think of that just for the time being. So what's going to happen is, in order to go against that, he's going to have to swim in that direction. We know that he can do 1 meter per second. So he's now going upstream. So just in terms of the language, this is all important. If he heads at an angle alpha to the upstream direction, so he's heading at that angle, this thing here is going to drag him down. So he's going to end up, it doesn't say that he goes directly across or anything like that. So very much not the scale here. It says that he's going to go, he's going to get swept down, and he's going to be swept down at an angle theta to the downstream. So downstream is right, upstream is left. Okay, so that's the general direction. I'm not saying that all happens in a second. Of course, it's 36 meters. So really, you know, we should be looking at 2 meters. But I think the bigger it is in the diagram, the better. So let's just word these things as we do them. Well, this vector here, that's the river or the current, whatever way you want to think of it. This is what he's actually going to be doing. So this is the man. That's what he'll be doing. And this is the direction in which he will be going. So this is what he'll be doing with respect to the river or the current. Okay, let's write in what we know. So the river or the current, that vector is the easiest one to write down. It is simply being moved to the right, being moved to, so it's 2i and 0 j's. If you haven't tried this already, do pause it, give it a shot yourself. Don't just sit there and sort of have me do it. It is like, as we would do in normal class, I would give you time to do this. So that is something that you should be adding on to the time with the video and so on. Let's see, what is V of M or? So we know that this thing here is alpha, and we know that the magnitude of it is just 1. So it's going to be 1 cos alpha. Now that's going to the left, isn't it? So it's minus 1 cos alpha I plus 1 sine alpha j. And that is in an upwards direction, so the j's are positive. Now it comes down to our guy here. Well, we don't know anything about this really, so we can just say that it's going to be h cos theta I plus h sine theta j. That's about as much as what we can say. Now we know this is the thing that we've been employing the whole time. The vector of the man relative to the river is the vector of the man minus the vector of the river. So it turns out that we can make this little equation here. Those are the two things we know, and this is the one thing that we don't really know anything about. So to get this thing here, we have to just add on these two vectors. So we'll add the I components together. So we get 2, and it'll be minus 1, so we'll just call it minus cos alpha. That's how many i's we'll have. And we'll add the j's, well, we just get sine alpha j. And if you compare it to this, cos theta I plus h sine theta j, okay, we know that it is equal to that, and this is the best way that we can write it. Now it turns out that h cos theta has to equal to 2 minus cos alpha, and sine alpha has to equal to h sine theta j. So what we can say is we can say that if we were to take tan theta is equal to sine theta over cos theta. That's something that you should know off by heart. Remember, this is opposite over adjacent, whereas sine is opposite over hypotenuse, and it's being divided by adjacent over hypotenuse. And if you multiply top and bottom by h on that particular one there, top and bottom by h, you do get over a. It's also, while we're at it, it's also equal to h, it's also equal to h sine theta over h cos theta. The h's would just cancel, and since we know h cos theta is 2 minus cos alpha, beg your pardon. And just trying to see if I've done anything silly here over sine alpha. I must have done something silly here. Let me just have a little bit of a think about that, because it's not what they said that we were going to get. Oh, yeah. Did I subtract one thing from the other? No, I added them. That's how many i's we got. Oh, yeah, sorry. Beg your pardon. Of course, what we were meant to be doing was we were meant to be getting sine, and the sine of theta is this one here. So it is, of course, sine alpha, and it's over cos theta, and h cos theta is this, 2 minus cos alpha. So there we go. That is the thing that we wanted to show. We want to show that tan theta is equal to sine alpha over 2 minus cos alpha. So yeah, that's actually why having multiple equal signs is just a bad idea, because you're having to look over a lot of things as you go along. It's just better just to have one. It's a little bit easier to see it, because I know that that's a common thing that they say, don't do math sideways, do it down the way. So that's just showing you how you can sort of lose track of which one am I comparing to which when I'm going to do it. Let's just look at the rest of it. It says prove that tan theta has a maximum value. I'm not going to do that part there, because you're going to have to wait until you've done calculus, trigonometric calculus specifically, in 5th year. I don't think that you've done that already, so I'm certainly not going to introduce you to trigonometric calculus. You'll have to do regular calculus first, but we will do that. I think that's probably a better in person. Basically what you want to do is you want to do differentiation here to show that one thing is the other. But it does say prove that tan theta is a maximum when alpha is 60 degrees. So they're basically giving us 60 degrees. Deduce that the time taken for the man to cross by the shortest path is 24 root 3. So what we want to do here is we want to just go and actually fill in fill in our values up here, and we can then just find out what it is that he is going to be doing. I'm just going to grab a calculator there. Hold on one sec. Just pause you. Okay, I've just got the calculator right there. So we want to find out what is this guy doing. Okay, what is Vm, as we were saying there, and we know that Vm is equal to this thing here. Okay, and since they're giving us what alpha is, we can actually just stick it straight into that. That's what Vm there is. So the man's vector is equal to 2 minus the cos of, and alpha is 60. That's how many i's he's doing. And it is sine 60 j's. That's what he's doing. Okay, feeling cos 60 is a half, but we'll type this in here. Cos 60 is a half. So he's doing 2 minus a half, so 1.5 for 3 over 2. 3 over 2 i's. That's what he will be doing. And this thing, I think, is root 3 over 2. If I've learned that off, sine 60, yeah. It's root 3 over 2 j's. Okay, so very annoyingly, I managed to stop the recording right there. So there's going to be a horrific jump. That was an accident. So I'm just going to have to tell you what I did. That's where we got to. We saw what the vector was for the guy swimming across. So that's what he is going to be doing when alpha is 60. So what we want to find out is what is this time to get across. Very common mistakes, getting the vector of him, which, that's his speed, therefore, distance 32, but actually he's going off doing something else here. We're only interested in what is his j vector, because we're only interested in getting across the 36 meter wide river. So it's only the j's, and he's doing that every second. So we'll just take out our fantastic triangle. Distance is going to be 32, and speed, it's not going to be the overall magnitude. It is just his j, his j velocity. So we just divided in there. I did a few bits and bobs. You can just throw it into your calculator if you like. I multiplied top and bottom by 2 there, just so you know, and I multiplied top and bottom by root 3. That's how I got that thing there. What I also was suggesting that you do was that you do question 24 is very similar to it, and 26. So those are the 2 trickiest questions in there. We've still got a bit to go on this. We've got to do apparent velocity of winds and stuff like that, but we will get to that. Okay, gents, take care.